Good morning, everyone. You will be hearing a presentation from Professor Jianzhi Chen. Professor Chen is currently an associate professor from You will be hearing a presentation from Professor Wenjuan Wu. Professor Wu is currently an assistant professor at the Department of Computer Science and Information Engineering, National Yilan University, Taiwan. Her research interests include Next, you will be hearing a presentation from Weizhe Jian. Professor Jian is currently an assistant professor with the Good morning, everyone. You will be hearing a presentation from Professor Jianzhi Chen. Professor Chen is currently an associate professor from National Yangming Jiaotong University. His research interests Good morning, everyone. You will be hearing a presentation from Professor Jianzhi Chen. Professor Chen is currently an associate professor from National Yangming Jiaotong University. His research interests include AIoT, 5G wireless communications and networks, robotics, and assistive application, and mobile computing. Today, he's going to give us a presentation entitled Using AI and V2X to Provide Driving Assistance. Ladies and gentlemen, let's welcome Professor Chen.
Good morning, everyone. My name is Jianzhi Chen from National Yangming Jiaotong University, Taiwan. Today, I would like to share some of our research results, in which we use AI and V2X to provide driving assistance. Here is today's outline. First, I will give some preliminaries for everyone to quickly understand the backgrounds. Then, the motivation of this research will be illustrated. I will also explain the proposed system architecture and methods. After that, the field trial and experimental results will be shown. Let you see what our team have done. Let's first imagine the situation when we driving a car on the road. As shown in the figure, assume we are in car A. Then we can see some vehicles in front of us, such as vehicle B, C, D, and E, and some are near to us, such as F, but out of our field of view. To protect ourselves, almost all drivers install a driving recorder for the cars. With traditional AI, vehicles in our field of view can be identified. A warning can be given when some vehicle is too close to us. An emergent warning is what multimedia AI can provide us. But is it possible to do more for a driver? Except the driving recorder, there are actually lots of sensors in a vehicle. If vehicles can share this information with neighboring vehicles with radio communications, for instance, information such as speed, driving intention, vehicle status, and its profiles, it will be helpful. In fact, we can do more to assist drivers with this radio and camera information to keep their safety. On the right-hand side of the figure, by fusing camera information and vehicle's profile and status information, we can identify each vehicle in the field of view and know their driving intention. For example, the white vehicle speed is 53 km per hour, and it will turn left after 20 meters. The black vehicle, car B, its speed is 42 km per hour, and it is braking. Through V2X communications, vehicle A can get its neighboring vehicle's information from received radio packets. These information are such as plate number, color, size, location, and driving status. Through multimedia AI, vehicle A can identify vehicles in front of it and get their information, such as plate number, color, size, distance, and angle. By fusing all this camera and radio information, we want to provide a more complete information to assist drivers' driving safety. Before going on, I would like to briefly introduce the concept of V2X for some of the audiences who are not familiar to it. V2X means vehicle to everything. The concept is that in the near future, vehicles can exchange information with other vehicles, with infrastructure, and with pedestrians via radio communications. There are three types of V2X. The first is vehicle-to-vehicle communications. In this case, two vehicles can communicate to each other directly. The second is vehicle-to-infrastructure. In this scenario, a vehicle can interact with infrastructure such as traffic signals. The last is vehicle to pedestrians. In this scenario, vehicles and pedestrians can exchange their information. So, vehicle to everything, V2X in short, includes all above scenarios, V2V, V2I, and V2P. So far, there are two main strings for V2X. One is DSRC, which is also known as IEEE L2.11p. The other is 3GPP LTE A Pro and 5G. Since release 14, LTE A Pro starts to support V2X. It is for sure that in the coming 5G era, 3GPP will still support V2X. So, future cellular system will provide strong ecosystem support for V2X. If any one of you are interested in the detail of V2X, you can study DSRC or 3GPP spec. Here I will not go into the detail of both protocols because of the limited time. In this slide, I use examples to explain our problem. I'm driving a vehicle. In my field of view, there are 4 vehicles in front of me. How do I know the driving status and the driving intention of this black vehicle? And others through camera and radio information. If there is only one vehicle in our field of view and this is also the only one among us, this question is simple. We will only see one red vehicle and only receive one kind of radio packet. Inside the packet, the vehicle shares its profile and says its speed is 60 km per hour. So, the radio information must belong to the red vehicle. We can pair the packet and the red car and then tag the red car with the driving status as shown in the figure. However, if there are 2 vehicles in our field of view, one is red, the other is silver. Also, we receive 2 types of radio packets. One says its speed is 60 km per hour. The other says its speed is 70 km per hour. Now, how do we pair the right vehicle with the right radio packet? Which packet is sent by the red vehicle and which of that is from the silver one? This question is hard because communication are usually non-line of sight. In fact, in a more general case, there would be more than two types of radio packets, because some of the neighboring vehicles may not be in our field of view, but near to us. So, this is a challenging problem. The processing procedure of our methods are described as follows. First, a deep learning algorithm keeps running to identify and tracking calls from the input video streaming. In our implementation, at that time, we use YOLO v3 for real-time detection and tracking. At the same time, each vehicle periodically broadcasts its profile and driving status via V2X communications. Car profile includes information such as plate number, color, car type, and GPS location. Driving status include vehicle's current speed, braking status, rotation, and turning status. Then, our methods fuse the camera information and radio information via pairing the vehicle object in the camera frame and the V2X radio packets. Finally, we tag right information to right vehicle object. This figure shows the original YOLO V1 model architecture. The full name of YOLO is You Only Look Once, means that for every figure, it can identify objects by one-time calculation. Too much iterative calculations are not needed, so it can support real-time object detection. Here are the detailed fusion procedure of our first method. We assume that each car is equipped with OBU and V2X communication interface. The onboard unit, OBU in short, is equipped with camera, GPS, and magnetometer. So, for vehicle A, its input includes the front camera's video stream, its own GPS location and orientation, and neighbor vehicles' radio packets received from V2X interface. Inside the radio packet, it is one of neighboring vehicles' profile and sensing information from the OBU. YOLO is responsible for processing the video stream. Sensing and received broadcast data will go through a data pre-processing procedure first. Then, for any possible pairing, for example, in this image, we can see 4 vehicles, B, C, D, and E. Since there are 5 neighboring cars, we will receive 5 different V2X broadcasting packets: B1, B2, B3, B4, and B5. Our goal is to pairing the vehicle object in the image with correct broadcasting packet. So, here we will first calculate the weight for any 2 possible pairing. Finally, the mapping decision algorithm will conduct the final pairing. Which pair right vehicle object to write car profile and driving status. Because of different notations, here we assume that we are driving vehicle X. Via OBU, the vehicle X can obtain its location and orientation. Vehicle X can also receive a number of broadcast packets from neighboring cars. We identify each packet by using notation BJ. Then, data preprocessing module will derive two features between X and any packet BJ. They are distance and angle. The equations are as follows. Here angle is a relational angle between vehicle X and BJ. This slide shows how weight calculation module derives the weight between any vehicle BJ in the field of view and any broadcast packet BI from the neighboring cars. In fact, the weight calculation is comparing the similarity of the content of a broadcast packet and a vehicle object in the camera. To calculate the similarity, we consider 5 features. The first one is the plate number. So in the first equation, we calculate the number of matched characters between vehicle BJ and broadcast packet BI. Here we normalize it by dividing the number of characters of a plate number. The second is the color of the vehicle. Here we calculate the square root of the RGB color difference between vehicle BJ and packet BI. Smaller difference will get a higher weight. The third weight is the car type. If the vehicle type of vehicle BJ and broadcast packet BI are the same, then the weight of car type equals to 1. Otherwise, the weight of car type is 0. The fourth weight is the distance. We calculate the difference in distance between GPS measure and camera measure. The weight getting large when the distance difference is small. The last weight is the angle. We calculate the difference in angle between a magnetometer measure and a camera measure. Finally, we sum up all the 5 weights to derive Wij, which is the weight when pairing vehicle BJ in the camera and broadcast packet BI sent by some neighboring car. Then, for broadcast packet BI, we define its confidence as follows. The confidence value is high when packet BI is very similar to one vehicle object and very different from the others. Here we design two mapping decision algorithms. One is short-term pairing, the other is long-term pairing. Short-term pairing considers only the latest camera video frame and receive broadcast packets. So, highest confidence value Ci of t will be paired first. For sure, packet Bi will be paired with the vehicle Vj star when Wij star is the highest weight in all Wij. And then the confidence value of the remaining broadcast packets. will be updated. After completing the update, the pairing procedure will be executed repeatedly. Compared to short-term pairing, the long-term pairing will consider the historical pairing result. The long-term pairing result will be stored in a vehicle LP of T-1. Each element in LP of T-1 is a triplet: BI, BJ, W prime IJ, where W prime IJ is a long-term weighting value. In the long-term pairing, we will take LP of T-1 and short-term pairing result SP of T into consideration. There will be 4 possible cases when we compare LP of T-1 and SP of T. The first one is that packet BI and vehicle VJ are paired together in both results. Then we keep the pairing results and update only W prime IJ of T as follows. Different from the first case, in case 2, we will find a broadcast packet BI is paired with different vehicles in SP of T and LP of T-1. For example, in short-term pairing, BI is paired with vehicle VJ, but in long-term pairing, BI is paired with vehicle VK. When this occurs, if 1 minus alpha multiplied by W prime JK is greater than or equal to Wij, then we keep the long-term pairing result as the final result. Otherwise, we update long-term pairing result by copying the short-term pairing result. That is, BI is paired with vehicle VJ instead of VK. Then we keep the pairing result and update only W prime IJ of T as follows. In case 3, we find a pairing result for packet BI, but we cannot find it in short-term pairing results. In this case, we will keep the pairing result in LP of T, but update its weight as the original weight multiplied by 1 minus alpha. This case may occur when the broadcast packet is not received by vehicle X because of interference, or when the vehicle VJ is far from the vehicle X at time T, so they cannot hear each other. The last case is that we can find a pairing result for packet BI in short-term pairing, but we cannot find it in long-term pairing result. For this case, we will accept this new pairing and insert it into LP of T. After above steps, we got the long-term pairing result LP of T for time T. Here, let's see a short film. In this film, we do field trial for above proposed method.
We conduct the field trial in a real-world scenario. 3 cars were equipped with GPS and IU sensors, one of which was equipped with Z camera to capture the surrounding images. By this field trial visualization, we've shown that through our data fusion and real-time V2V communications, we can let a car visually see the driving status of its surrounding cars.
Okay. Here are some details of our field trial. As shown in Figure A, before using our data fusion algorithm with Camera AI. With Camera AI, we can only identify vehicles, track vehicles, and get camera measure distance and orientation. With our data fusion algorithm, because car B and car C share their information with V2X communications as shown in Figure B, we can correctly tag each of their car profiles on the right car. Since car A is not equipped with V2X interface, no car profile is tagged for it. Like above two figures, Figure C and D show similar results, before and after data fusion results. In above field trial, we proved that our idea can work on the real road, but we found two problems. The first one is that we take lots of time for the experiments, but only get very limited data sets. The other is that collecting such real data set costs lots of money. In fact, in that experiment, we hired two Uber drivers for several days and do the experiment. To collect data sets, a traditional way is that the researchers driving their vehicles on the road and then collecting the sensory data of the vehicle and the front camera's video or LiDAR data. After getting the real data sets, we can take them back to the laboratory and test the design algorithm's performance. However, by this way, we can only get limited data sets and limited scenarios. So, to solve this problem, we have developed a simulation platform that enables V2X communications. And then, via the platform, we can collect rich kinds of data sets by simply changing the simulation parameters and doing simulations. To develop the simulator, we use the open source platform Kala as the base, and then extend and implement several modules to build a V2X simulation framework. Here I will not spend too much time to explain about the detail of the simulator. This figure shows the system architecture of the simulator. The simulator is composed of three layers: configuration layer, sensor layer, and the output layer. In the configuration layer, there are four modules: weather module, map module, spawn module, and self-driving modules. The weather module is responsible for producing different parameters for different weather. Weathers such as sunny day and rainy day are provided. The second module in the configuration layer is the map module, or called geographic information module. It is to provide different road maps and geographic information. Here are some examples. Spawn module, or the vehicle flow module, can support us to generate different degrees of vehicle flows. Here are the examples of light traffic, medium traffic, and heavy traffic. The last module in the configuration layer is the self-driving module. In the module, the developer can develop his or her own autonomous driving algorithm or use the default method. The sensor layer is divided into three modules. They are the camera image module, V2X communication module, and sensor module. The camera image module is to collect the image data of the main vehicle. Here we can see some examples. The figure in the left-hand side is the front camera view of the main vehicle, and the figure in the right-hand side is the back camera view. The second module is the V2X communication module. The module is responsible to simulate V2X communications. Currently, we support Wi-Fi and cellular V2X communications. The module is developed by referring to the real statistical results. So, the delay and jitter characteristics of these radio communications are considered in this module. The last module in the sensor layer is the sensor module. So far, GPS sensor, speed sensor, and orientation sensors are supported. The only module in the output module is the dataset generation module, which logs the image and sensor readings of the main vehicle and records the profiles and sensory data of surrounding vehicles from the V2X communication. Finally, the dataset generation module will package this log data as the data sets. So, with the simulator, we can get data sets in rich bound of scenarios, such as different road maps, different degree of vehicle flows, light traffic, medium traffic, and heavy traffic. Using these data sets as the input, advanced algorithms can be tested and check the performance in different scenarios. So here, let me show a use case of the V2X simulation framework by redoing the aforementioned experiment. As shown in the right-hand side, here are some frames from our simulated datasets. We have also redone the experiments to evaluate our fusion algorithm. From the figure on the right-hand side, we can see that the car profiles are correctly tagged on the right card. Here, 97, 25, and 137 are these vehicles' virtual plate numbers. In the following, we would like to solve the same problem but with more AI. Here, in the red box, we show an alternative architecture of our second method. We design a mapping decision feedback neural network, MDFNN in short, which is inspired by RNN. The input data is the sensory data of vehicles and the mapping decision results in the near past. Via the MDFNN, we can position the vehicle in a frame for each broadcast packet. In the image, we can also position the vehicle objects with Euro. Then both results will go into the mapping decision block. The block will map and fuse both results. This is the network model. This is how we design the MDFNN. Input data is the sensory data of vehicle X and broadcast packet BI, and the past mapping decision result of BI. Here we illustrate the concept of our car position estimation method MDFNN. The input of the MDFNN include the location and speed information inside packet BI. Vehicle X speed and orientation, and the past positioning result of packet BI. All these input data are all normalized. Then MDFNN will predict the current position of BI as shown in the figure. Okay, let's check an example and see how the whole system works for a packet BI. Assume the packet BI is sent by the black vehicle, but how do we identify BI is sent by it and then tag inside information with the black car? We will divide the whole screen into grids. For example, this image is divided into 5 by 5 grids. Each cell in the grids is mapping to a neuron in the MDFNN. Okay. Since BI is sent by the black car, so the ground truth shall be like this. The grids which contains the black car, the value will be 1. Other grids will be 0. Here we have to note that there is one more neuron called outside. This is for the packet from the vehicle which is not in our field of view. So, if the MDFNN is well trained, after the calculation of MDFNN, we will get a result like this. Here we can try to position the packet PI. We can see there are higher probability in these 4 grids. MDFNN thinks the owner of packet BI shall be in these 4 grids. Euro also generates an output like this. It identifies there are 4 vehicles in the frame. MDFNN positions the target vehicle using sensory data BI. Euro also identifies vehicle objects on the screen. Then, in the mapping decision phase, It is responsible for deciding which car in the image is the target vehicle of packet BI. Obviously, there is a large probability that packet BI's owner is the black car. Then we can augment the vehicle information and driving status on the black vehicle. Here is the loss function we designed for NDF-NN training. There are two parts. One is the loss for the grid in image. The other is the loss for the outside area. Here is our experimental results by using our simulated data set. Let's see. Okay, so how about the accuracy? Here is the setting of our experiment. We deploy 5 cars surrounding the main car. We take image and receive broadcast packets once per hour. The car only receives broadcasts from cars which is near enough. The distance needed to be less than 30 meters in our setting. There are about 1,400 images and 6,700 broadcast packets in the dataset. We can see that compared to RNN and baseline method, our method can get an improvement by about 30% accuracy. Here we can also see the effect of grid numbers. As the grid number increases, the accuracy also raises, but the performance converges after 11 by 11 grids. In this speech, we discuss an interesting vehicle object and the broadcasting packet pairing problem. Two methods are proposed. One is AI for object detection plus algorithm-based fusion, and the other is an almost AI method. With simulated data set, we show that both methods can work. Okay, thank you for your listening. If you have any question, you can give me a mail. My email address is as follows. Okay, this is my email address. So any question?
Good morning, everyone. you will be hearing the presentation from Professor Wenjuan Wu. Professor Wu is currently an assistant professor at the Department of Computer Science and Information Engineering, National Yilan University, Taiwan. Her research interests include image processing, data compression, interactive multimedia, information security, IoT, and STEM education. Today, she's going to give us a presentation entitled Implementation of Intelligence Traffic Violation Report System. Ladies and gentlemen, let's welcome Professor Wu.
Hello everyone, my name is Wenjuan Wu. I am from National Yilan University. Today I will like to share my experience on applying IoT technology to the traffic violation report. The title is Implementation of Intelligence Traffic Violation Report System. This system is mainly to improve time-consuming field editing, so that manual reporting of traffic violation is faster. In this way, it can also maintain road safety and reduce traffic accidents. Transportation in Taiwan is quite developed and convenient. To reach other cities, people can take public transportation, such as mass rapid transit, MRT, bus, and taxis, or use motorcycles and cars to allow them to move quickly. However, private cars are still generally used in transportation. According to statistics, it is found that the high density of motorcycles in the world is in Taiwan, with almost one per person. On average, there are 2 motorcycles per family. This is the family field Skoda waterfall in Taipei, which once appeared in the National Geographic Travel Photo Contest. The main reason is that it has high mobility and is not easily affected by traffic jams. So motorcycle has become the primary transportation tool for most commuters. The number of private cars in Taiwan has been increased significantly in recent years. There was an increase of 116,000 cars in total, from 1216 to 1218. Nearly 16% of family owns a private car, and nearly 13% has 2 private cars. On average, there are 1.5 private cars per family. During the holidays, Taiwan's highways always turn into free parking lots, just like the 2 pictures. Because of the explosion of automobiles and motorcycles in Taiwan, currently it has resulted in many traffic violations, such as illegal parking, running a red, yellow light, wrong-way driving, lane change without turn signals, speeding, and so on. This may lead to traffic accidents and even increase the casualty rate.
驾驶打方向灯要起步，这时后方机车被逼上内侧快车道，其中一名女骑士疑似和灵车擦撞，失控倒地。虽然后方机车紧急刹车没有撞上去，但这名女骑士却倒地不起。
Based on the statistics from New Taipei City, the incidence and the mortality of traffic accidents in 2019 increased by 32.23% and 33.06% respectively compared with the previous year. In order to maintain road safety and to reduce traffic accidents, police and people both can feel evidence for traffic violation through digital tools such as smartphone and dash cam. In this table, it shows the statistics of traffic violation reported by Taipei City from 2015 to 2019. It can be seen that the number of reports is increasing year by year, and the more health of violation are cars. This table is the reporting statistics of New Taipei City, also from 2015 to 2019. It can be seen that the top 3 reports of violations in the past 5 years are parking violations, speeding, and running red lights. Nowadays, people can use car dash cam to record illegal videos on the road and then submit this to traffic violation reporting website. This figure is a flow chart to report traffic violation. First, it is necessary to log into a reporting website and then fill in the personal information of a reporter, such as name, ID number, email, contact mobile number, and address. And then the system will verify the reporter. Second is to provide the evidence, date, time, and location of that violation must also be attached to the evidence information. The 2 figures are the website for reporting traffic violations in New Taipei City. The evidence private must have complete violation facts, such as video clips or multiple consecutive photos. License plate and the ground marking must be clearly identified. This figure shows 4 cases of traffic violation, including illegal parking, running red lights, overtaking prohibited, and the ride without a helmet. Figure D provides a single photo as evidence, but in other cases, it should be to provide more than 3 consecutive photos or video clips. However, the volume of video data in a car dash cam is quite huge. A 128 GB memory can store almost 415 videos in high quality for a total of 22 hours. If the video file of 3 million is added manually, it will take 3 to 5 minutes on average. The time cost of edited video is very high. In order to speed up the video edit work of traffic reporting, we adopt multiple IoT modules so that violation chips can be automatically stored when driving. This figure is a diagram of our hardware system architecture. It is designed to use a single chip microcomputer, Raspberry Pi, and the IoT module such as input module, camera module, and the voice module are connected with Pi, and this device is placed in the car. If the driver finds a violation of car, he can press down the button or give instruction to the Raspberry Pi via a voice module. The Raspberry Pi will start the Connect camera to record video. Here, the length of a video clip is 10 seconds, and the file capacity in MP4 format is about 5 MB. Then our system uses recron technique to mount to the cloud service of Google Drive and upload these video clips to the private cloud space synchronously through the Wi-Fi wireless network of the Raspberry Pi. The reporter can download these video materials after return home and upload to the reporter website together with the reporter personal information. We use a Google AI BIOS kit to simulate the traffic violation reporter system and connect it to the Raspberry Pi 4 Mode B and a camera module. This voice kit contains an arcade-style push button, a voice head accessory board, a microphone board, and a 3-inch speaker. This is the process of device installation. Here is the speaker, and this is the button module. This is the microphone extension. Here is the implementation result for our traffic violation report system, and it displays 4 views of this device, such as top view, front view, left view, and the right view. There is a push button for input on the top. When a camera is in front of the button, as shown as this figure, that AI kit in a box has been already connected to Raspberry Pi, a voice headboard, and a speaker. They only need to connect to the internet and powered by a portable charger, as shown in the 2 figure, to start Raspberry Pi. These are the existing smart speaker products, including Google Home, Amazon Echo, Apple HomePod, and so on. Here is the operation process or smart speaker. First is to wake up device, like "Hi Google." Second is to convert user speech to text. And the next is the dialogue management. In the end, output the understood text into speech. Here we first demonstrated the voice operation of Google AI Voice Kits.
Okay, Google, what's the time right now?
It's 11:53.
Seems to work. Okay, Google, what is the capital city of Pennsylvania?
Harrisburg is the capital of Pennsylvania.
Okay, Google, who wrote The Hitchhiker's Guide to the Galaxy?
Douglas Adams, Owen Colfer, and Adams Douglas wrote The Hitchhiker's Guide to the Galaxy.
First, we use Snowboy to wake up AI voice device. Snowboy is a high consumable wake-up word detection engine to create your own hardware, like OK Google or Alexa. It has the following property. Highly customable. You can free define your own magical phrase, like open door, turn on the light, or hello dream house. The second property is always listen, but protect your privacy. Another property is lightweight and embedded. It even runs on a Raspberry Pi and consumes less than 10% CPU. This is a part of Python code, which is always listening and detecting the web word Snowboy. User can log in to the Snowboy website to change their own hardware. User can click the button to create hardware and then to record your voice 3 times. Step 2 is STT. That is speech to text. Here we use speech recognition API of Google to recognize speech into text. And in the last step is TTS. That is text to speech. Contrary to STT, it is to convert the understood text into speech and output it. Between STT and TTS, there is a step to understand user natural language. Here we use an NLP tool. That is Dialogflow, provided by Google. This tool is used to understand what a user says. Dialogflow is used to build an engine AI to distinguish empathy and intent in the sentence. When a user says, "How is the weather tomorrow?" or Will it rain in Taipei next week? It means that empty is date or location, and the instant is the weather. So user can log in to the Dialogflow website and create a new engine. And then click it to create a new empathize. For a certain entity ID, user can key in the similar word with the same meaning in here. And then to build an entity. Next is to add the chaining phrase to chain the intent. To chain the intent with what a user may say. In this way, the built agent AI will distinguish entity and intent in the sentence. During the experiment, we actually drive a car around 10th Street in New Taipei City for an hour. This figure shows the path of our driving. Our route goes through downtown street and alleys. And this device is recommended to be placed here, near the steering wheel. Allow the driver to operate quickly. Here we show the completion result of 3 row sessions. This feature on the left is the static result taken by our system, and the picture on the right is the static result of a dash camera. Both of them show the start date and the time on the picture. The dash cam used in the car is the MIOC 350, and its resolution is as high as 8020 by 1080p. Here is the result on facing row. Compare left picture with the right picture. The license plate captured at the same time is still clear and identifiable. This is the result of Zhongshan Road in Tanshui. The left picture shows that a 10-second clip is able to record the violation by using our system when the 2 consecutive cars parking illegal. And this is the result on Zhongshan Beilu in Danshui. Only when the sunlight is very sufficient, such as the 2 pictures, the license plate captured by our system is too blind to be recognized. This problem will be improved by using high-quality camera module. Here is to show traffic video clips recording using our system, which are stored in the private cloud space of Google Drive. The reporter can download these videos when return home and upload to the report website together with the reporter personal information. In our simulation, a total of 19 video files were stored on the cloud platform, and each video is 10 seconds in length. Here is to show the success rate of voice instruction using our system. In our system, the instruction snowball is used to wake up the device. There are a number of 46 success. So the success rate is 92%. And we use 3 instructions about 开始录制 in Chinese, start record in English, record in English. By using the 3 instructions to control the Raspberry Pi to rec the video. From this table, it can be seen that when the voice instruction is longer, it is easier to recognize successful. That is, the success rate is higher. In the end, I would like to make some conclusions for today's presentation. In this implementation, IoT technology is used to connect multiple modules, such as button module, camera module, and the voice module, to communicate with each other. When a drive discovers a violation, he can operate the input module or voice module, and then the camera will be active to record a video clip. These videos and the related information such as day, time, and the GPS location will be automatically uploaded to the specific private cloud space, which can reduce the time cost for the reporter to report traffic violations. After the simulations, it was found that the 80 clips can be successfully used on the violation reporting website, and the reporter saves nearly half of processing time to edit the video in the dash cam. This is my presentation. Thank you for your attention. If you have any question about this presentation, please
Next, you will be hearing the presentation from Wei-Zhe Jian. Professor Jian is currently an assistant professor with the Department of Computer Science and Information Engineering, National Donghua University, Taiwan. His research interests include wireless, rechargeable sensor networks, 5G mobile networks, AIoT, fog computing, and cloud computing. Today, he's going to give us a presentation entitled Deep Learning Networks for Cellular Traffic Prediction in the IoT. Ladies and gentlemen, let's welcome Professor Jian.
Hello everyone, my name is Wei-Zhe Jian. I'm an assistant professor. I'm coming from National Donghua University, Department of Computer Science and Information Engineering. It's my great pleasure here today to share my research results. Before I talking about technology, I would like to express my sincere thanks to the people, especially Professor Huayan Chen, who invited me to share my research results. Okay, the title of today's presentation is Lightweight Deep Learning Networks for Cellular Traffic Prediction in IoT. As you guys didn't know who I am, let me introduce myself. I just graduated from National Chen Gong University in Taiwan in 2020. So I just graduated for a year. I'm a brand new professor now. I'm also a Deputy Secretary General in Institute of Information and Computer Machinery in Taiwan. Therefore, if you are a master student or a PhD student, you may consider to submit your thesis or your dissertation to our society. We have best thesis award and the best dissertation award every year. I'm also associate editor for HCI's ZIT, IEEE Networks, and JLC. Welcome to submit your paper to the journal. Okay, I would like to divide my talk into 6 sessions. First of all, I would like to introduce why do traffic prediction problems need to use the lightweight deep learning model and what are benefits. In session 2, I would like to introduce the current study of cellular traffic prediction, which are based on deep learning. Then I will come to propose a lightweight model called Lightweight Spatial Temporal Convolution Neural Network Model. In next session, I will present result analysis. Finally, I will conclude my talk with several highlights. Let's talk about what the traffic prediction problem is and why we need to use a lightweight deep learning model. The left figure shows the evolution of mobile data consumption, and the right figure shows mobile backhaul traffic growth bandwidth. We can see that the rapid development of multimedia, smart city, IoV, and other IoT applications have led to an exponential increase in data traffic year by year. According to this trend, the cellular network will become more and more congested, and the quality of service of users may decrease. According to the traffic prediction result, we can know which area have more traffic demand and adopt some strategies such as adding base stations or allocating network resource. Therefore, let's talk about traffic prediction method, which can be divided into two types, including physical methods and statistical methods. First type, meaning utilize the laws of physics and user behavior to achieve predictions. The second type focuses on exploiting the relationship among historical data, which are adapted to establish the prediction model. In general, the physical method has advantages in long-term prediction. In contrast, the statistical method is better in short-term prediction. Moreover, there are many applications based on cellular traffic prediction. Most of them have strict requirements, such as industrial Internet of Things. Accurate traffic prediction in short-term prediction is needed to avoid unexpected situations, so it is suitable to use the statistical method. The statistical relationship in the historical data could be modeled by various methods. It can be classified as linear models, such as autographic models, moving average models, and autographic integrated moving average model, and nonlinear models, such as artificial neural networks, recurrent neural networks, long short-term memory, and get recurrent unit. However, large-scale and high accuracy cellular traffic prediction is extremely challenging. The reasons are as follows. For temporal dependencies, cellular traffic will change over time due to user behavior, network applications, and diverse network requirements. For spatial dependence, data traffic includes mobile users and static users. Mobile users introduce spatial dependence into the cellular traffic among base stations. In other words, when a user is moving and using a service at the same time, the spatial dependence of cellular traffic will affect the prediction results. For spatial temporal dependencies, there are many factors, including population, building holidays, and various social activities. These influential factors further complicate spatial temporal dependencies and influence cellular traffic. To exactly predict cellular traffic, deep learning is a promising technology. Although using ARIMA can find the solution that closest to optimal solution with lower complexity, the performance of STM over ARIMA in general, especially when the training data is sufficient. However, ARM-based method cannot process the spatial temporal dependencies problems. Some researchers use hybrid method to solve this problem. The prediction performance is well, but these methods are complex and contain many parameters. In other words, these deep learning methods often require many computational costs, memory, and energy to train a model. For the cellular traffic prediction problem, real-time prediction is required. If each base station is equipped with high-speed computational capacity equipment, it is a lot of cost for the operator. Therefore, a lightweight deep learning model is a suitable solution. Deep learning models can be compressed by methods such as pruning, quantization, joint training, and distillation. However, different deep learning model comparison methods are suitable for different problems. In this research, we aim to develop a lightweight deep learning model for the cellular traffic prediction problem. There are three main contributions of this research. We consider spatial temporal dependencies among base stations and propose a lightweight deep learning model for cellular traffic prediction problem. We optimize the hyperparameters of the proposed lightweight deep learning model. The second contribution is that the proposed architecture and the model can reduce the operator's equipment cost and save the calculating cost. And then let's talk about the current study of cellular traffic prediction. The temporal dependence of traffic has been discussed in many studies. Most of exciting methods to solve this problem are based on architecture of recurrent neural networks. However, the recurrent neural network architecture is difficult to achieve parallel computing and is with a bunch of parameters. Although recurrent neural network architecture can effectively capture temporal features, it cannot solve the problem of spatial dependencies of cellular traffic data. Therefore, researchers will propose different models to solve the spatial temporal dependence problems, which can be simply divided into single models and hybrid models. In single models, DenseNet was proposed to predict cellular traffic. DenseNet is a densely connected CNN, which models the traffic of different base stations and capture spatial temporal dependencies of different base stations through convolution operations. However, DenseNet is very memory intensive. In hybrid models, the architecture of autoencoder connected to LSTM has been proposed. LSTM is adapted to extract temporal features, and autoencoder is used to extract the spatial features between different base stations. However, the encoder will compress extract features, which may destroy the spatial temporal features of neighboring base stations. Next, I will introduce the problem definition for traffic prediction. For a cellular traffic prediction problem, our first goal is to propose a lightweight architecture that can consider the spatial temporal dependencies of traffic data. The second goal is to achieve high accuracy predictions. The third goal is to minimize the hyperparameters. In order to achieve the three goals just mentioned, we propose lightweight spatial temporal convolutional neural network model for cellular traffic prediction. And let's talk about this method. This is the flow chart for the research. First, pre-process the network traffic data. then use the LSTCNN model we proposed for training, and finally analyze prediction result. Next, let's talk about our traffic data. We use this data set as test data, which is from the European telephone service provider Telecom Italia. The dataset was collected in Milan from November 10, 2013 to January 1st, 2014. This dataset is temporarily aggregated every 10 minutes. There are a total of 10,000 base stations in this dataset. We take 900 of them as input data and split the data into 90% training data and 10% testing data. There are 11 hyperparameter settings are adjusted to improve prediction accuracy. In order to consider the spatial temporal dependence of traffic data at the same time, we design a lightweight neural network model based on CNN, but CNN can only capture the data features of the region. Therefore, in the data preprocessing part, we have performed some conversions so that LSTCN can capture the features of spatial temporal dependence of traffic data at the same time when performing convolution operations. On the right figure is a segmentic diagram of network traffic. Each grid represents a base station, and the value of the z-axis represents the network traffic at the time interval t. We convert the original two-dimension array into a one-dimension array by equation 4. Next, we merge the converted one-dimension arrays. For example, the traffic data of time unit 1, 2, 3 is first converted from two-dimension to one-dimension array. Then merge the network traffic data of these 3 units of time into a two-dimension array. Okay. This is the process of our data preprocessing. Through such data conversion, when performing convolution operations, the temporal dependence features can be extracted from vertical axis, and the spatial dependence features can be extracted from the horizontal axis. We evaluate the performance of cellular traffic prediction based on 3 metrics, including mean absolute error, root mean square error, and mean absolute percentage error. Next, let's talk about the proposed lightweight neural network model. There are many cellular traffic prediction methods that have been proposed. High accuracy prediction results are usually accompanied by high computing capacity requirements. In order to reduce the cost of high specific equipment, we evaluate and analyze the lightweight mechanism of MobileNet v3 and design and appreciate the lightweight neural network model for the network traffic data after data preprocessing. Since the lightweight methods are easy to destroy the structure of the raw data, not all mechanisms are applicable. This table shows the lightweight mechanism used in this study. Width multiplier and the resolution multiplier can reduce computational cost and the number of parameters through controlling the input width of a layer and the input image resolution. But it will destroy spatial temporal features. Therefore, we didn't adopt these two lightweight methods. Pooling layer is usually used after convolution layers. Average pooling and maximum pooling are commonly used methods. Generally, the error of feature extraction mainly comes from two types. First is that the variance of the estimated value increases due to the limited size of neighborhood. The second is that the error of estimated average value is caused by the deviation of parameters in the convolution layer. Average pooling can reduce the first type of error and more retain the background information of image. And the maximum pooling can reduce the second type of error and more retain the textual information. However, this method will destroy spatial temporal features. Therefore, we didn't adopt these lightweight mechanisms. The advantage of batch normalization is that after normalizing the features of each layer, we can ensure that the static of output of each layer is fixed. It can avoid the mutual influence of different layers when adjusting parameters. Batch normalization can speed up training and prevent the problem of gradient vanishing. However, batch normalization depends on the batch size. It is unsuitable in this problem. According to our input data format, we adopt the following mechanism to implement a lightweight model, including linear bottleneck, depth-wise separable convolution, point-wise convolution, inverted residual sequence and excitation, and edge switch. The linear bottleneck consists of point-wise convolution and depth-wise separable convolution. It can replace traditional convolution layer to reduce parameters and calculations. The traditional convolution is that each kernel map needs to do convolution with all channels. Linear bottleneck separates it. Point-wise convolution only does 1 times 1 convolution for all channels, which is used to run features between channels. The depth-wise separable convolution uses different convolution kernels for each input channel. In other words, it only maps the spatial temporal of traffic data and not cross-channel correlations. Moreover, the architecture of the inverted residual is the opposite of traditional residual structure. First, the input feature map is enlarged by 1 times 1 convolution. Then, 3 times 3 depthwise separable convolution is used to perform convolution operation. And then finally, the 1 times 1 convolution is used to reduce its dimension. The advantages of inverted residual are multiplexing features and mitigating feature degradation. For a cellular traffic prediction problem, traffic data of each base station has spatial temporal dependence. So we propose a spatial temporal input data format based on convolution neural network architecture. In order to avoid feature data being destroyed due to compression, this research proposes a lightweight convolution neural network model, including 2 traditional convolution layers, 5 linear bottleneck layer, and inverted residual layer. First, we use a convolutional layer to get spatial temporal features. Generally, if the tensor dimension is lower, the multiplication calculation of convolutional layer is smaller. The overall calculating speed will be very fast when the entire neural network is a low-dimensional tensor. However, if the filters of convolutional layer use low-dimensional tensors to urban features, it is hard to extract enough overall information. Therefore, we may prefer a high-dimensional tensor to urban features. The computational complexity and the high-dimensional tensor become a trade-off problem for lightweight model design. In order to capture the feature more deeply, a 5-layer bottleneck with expansion factor architecture is used to connect the convolution layer. This is the lightweight model proposed in this research. In each bottleneck layer, point-wise convolution, depth-wise convolution, and point-wise convolution are included in the sequence. The first layer of point-wise convolution is also called expansion layer. It is used to expand the dimension. The third layer of point-wise convolution is also called the projection layer. It is used to compress data and make the neural network smaller. Since both the expansion layer and the projection layer have parameters for learning, the entire neural network structure can learn how to better expand data and recompress data. Finally, convolution layer and the fully connection layer are connected. Next, we further explain the mechanism in each bottleneck layer. Each bottleneck layer has has three lightweight mechanisms, including depth-wise separable convolution, screens and excitation, and inverted residuals. The depth separable convolution is composed of two point-wise convolution and depth convolution. And let's talk about the performance evaluation for cellular traffic prediction. We evaluate the proposed lightweight model with Google Colibri, the simulation tool Adobe Class. The details are shown in this figure. These two figures show the traffic prediction results of two types of base stations. The first type of base station has a large traffic range, but the traffic is distributed evenly. The second type of base station has a small traffic range, but the traffic varies greatly. We adjust the hyperparameters to observe the prediction results of these two types of different base stations to optimize the proposed lightweight model. This slide shows the experimental results. The blue line is the original data, the green line is training data, and the red line is testing data. And we can see that for base stations with stable traffic changes, the prediction effect is very good. But for the base station with drastic changes in traffic, the prediction result can be improved. The figure shows a comparison of batch size from 2 to 412. A large batch size can reduce training time and improve stability, but it will result in a decrease in the generalization ability of the model. In our experiment, the batch size is set to 32 to achieve the most accurate prediction. The figure shows the comparison of the optimizers, including RMS proper, ADA grade, ADA max, and ADAM. ADAM combines momentum and ADA grade. Therefore, ADAM returns the characteristic of momentum that the learning rate will be first in the same direction dimension, and the learning rate will be slower when the dimension changes. In addition, ADAM also adjusts the learning rate of the square value of the path gradient. Each learning rate will have a certain range, which will make the parameter update more stable. Therefore, we choose ADAM as the optimizer. The figure shows the comparison of the time step. The time step affects the extraction of temporal features. The large time step will cover the traffic information for multiple intervals. Relatively, it will increase the size of input data and the training time. In this study, it has the best prediction performance when time step is set to 3. The right figure shows the comparison of number of filters from 16 to 96. The left figure shows the comparison of convolution kernel size from 3 times 3 to 9 times 9. For the traditional convolution layer, the number of filters and the kernel size is positively correlated with the features that can be captured. But more filters or large kernel don't mean higher accuracy of traffic prediction. On the contrary, it will increase the training time. The suitable number of filters and the kernel size in this research is 32 and 3 times 3. The figure shows the comparison of threads. Using thread can greatly reduce the extracted feature map, which can reduce the calculation of the model and adjust the size of each layer of the neural networks. However, a big thread may cause problem of insufficient features, resulting in reduced accuracy. In this research, 5 threads have the best accuracy. The table is the comparison of the bottleneck block types. We tested the 4 types of depth of bottleneck block, including shallow deep type and deep shallow type, shallow deep shallow type, and deep shallow deep type. Experimental results shows that the architecture of the type 3 has better performance. The table shows the comparison of different activation function types. 9 different types of activation function are designed according to the type of bottleneck block. We test the result of using ReLU for all convolution layers. It's type 1. ReLU 6 for all convolution layers. It's type 2. H-switch for all convolution layers is type 3. And using them together from type 4 to type 9. ReLU and ReLU 6 will destroy the features when input data is a negative number, resulting in lower prediction accuracy compared to H-switch. Therefore, we used 3 commonly used activation functions to test and compare results. Finally, the type 5 architecture is used in this research. We also compare the different SE types. We test the utility of SE in different linear bottleneck layer and found that the use of global average pooling by SE will cause the destruction of features and lead to poor prediction results. Therefore, this study didn't use SE. There are some hyperparameter settings. Please refer to the list table. In order to evaluate the proposed library model, we compare it with the current technologies, including ARIMA, getter recurrent unit, long-short memory, self-attention, convolutional neural network, and so on. We can find that our proposed method has better prediction results. This figure shows the prediction results of the second type of base station. We can see that the proposed model also have good performance. Finally, we compare the performance of proposed lightweight model with exciting technologies which are based on the convolutional neural networks. Most of the methods for network traffic prediction use the architecture based on both recurrent neural network and convolutional neural network to capture spatial temporal feature. But the architecture of residual neural network require a lot of parameters, which means that it is difficult to achieve real-time training. In order to predict the traffic of massive base stations at the same time, consider spatial temporal features, and design a lightweight model. We pre-process the input data as a spatial temporal sequence for cellular traffic prediction. By adjusting the hyperparameters and architectures, the proposed lightweight model can not only avoid destruction of features, but also improve the accuracy of prediction and reduce the model size of the proposed lightweight method at the same time. In addition, compared with other related methods, the parameters, flops, and training time are also significantly reduced. Furthermore, in order to optimize the prediction performance and reduce the parameters of neural networks, we also use a meta-heuristic algorithm to adjust the hyperparameters. We use the simulated annealing algorithm to optimize the hyperparameters of the convolution kernel size, the number of convolution kernels, and convolution strides. A flow chart of hyperparameter adjustment strategy is shown in the left figure, and the right figure is the proposed algorithm. The figures show the comparison of MSE and parameters. The red line is the greedy algorithm. The blue line is the simulated annealing algorithm. Greedy-based algorithm shows a relatively stable downward trend, while simulated annealing algorithm have the opportunity to accept poor solutions at an early stage to avoid quickly falling into local optima. The result shows that the simulated annealing-based algorithm can get better accuracy and fewer parameters. The table is the comparison of parameters and accuracy. The first method uses the empirical rule to adjust parameters. The second is to use the greedy-based algorithm. The third is to use the simulated annealing-based algorithm. The simulated annealing-based algorithm has higher accuracy and fewer parameters than empirical rules and greedy-based algorithm in terms of accuracy and parameter quantity. There are many hyperparameters that need to be adjusted by deep learning model, but the empirical rule is difficult to achieve good results. The simulated annealing-based algorithm method can search for better hyperparameters, but the search process requires additional training time. In this study, the simulated annealing-based algorithm needs to use more running time than greedy-based algorithm. Or better result can be obtained by using this method to adjust hyperparameters. It takes extra time to train the model for the first time. Finally, I will conclude my talk with several highlights. This research considers the spatial temporal dependencies of cellular traffic to design a lightweight model called LSTCNN and optimize the hyperparameters of this model. Compared with the related spatial temporal neural network model, the proposed model can greatly reduce the parameters, throws, and training time while maintaining a certain accuracy. And in order to reduce the computational resource for cellular traffic prediction while maintaining a certain degree of accuracy, this paper proposed a hyperparameter optimization strategy based on a simulated annealing algorithm for lightweight neural network. Although we can get the better performance, but the assay-based method also need to take extra time to train the model for the first time. This is conclude my talk. Thank you everyone for joining me with this session.